Today, let us consider designing of another pipeline architecture. You know that if we want to multiply two matrices, let us assume that we have got two matrices A and B, and we want to multiply the two matrices to generate a third matrix C. So, the matrix multiplication is multiplying two matrices A and B to generate the third matrix C. We assume that these matrices A and B both are of dimension 3, that is, they have 3 number of rows and 3 number of columns. So, for matrix A, the elements are A11, A12, A13, A21, A22, A23, A31, A32 and A33. This is matrix A, and similarly matrix B is also of dimension 3, given by B11, B12, B13, B21, B22, B23, B31, B32 and B33. And you all know that if we want to multiply these two matrices, our resultant matrix will be given by every ijth element in matrix C is given by A I k multiplied with B k j, sum of k equal to 1 to 3. Okay. And if we write a program for creating this matrix C, the program will simply look like this, that for I equal to 1, 2, 3, do for j A I k. So, it is C I j equal to C I j plus A I k into B k j, and before this at this point I have to initialize C I j to 0. Okay. So, I need such a for loop to compute this matrix C. Okay. And you find that here the complexity of this matrix multiplication root n will be 3 into 3 into 3, that is 27 number of operations. Okay. Now, let us see whether we can design a pipeline architecture so that I can multiply this matrix in less amount of time. So, for this pipeline architecture, I assume that every element in the pipeline architecture is having a function like this. It has got 3 inputs, A, B and C, and it provides 3 outputs. In the horizontal and vertical directions, whatever is the input, the same thing comes as output. So, here the output will be A, here the output will be B, whereas in the diagonal direction, the output will be C plus A into B. Okay. So, this is the processing element using which we will try to implement, try to design a pipeline architecture so that I can multiply these 3 by 3 matrices. Okay. So the architecture will be something like this. Okay. So as we have said that every such processing element will have 3 inputs. One we represent as horizontal input, the other one as vertical input, and we have a diagonal input. Okay. So it is like this. The interconnection will be made of this form. Okay. So this is the type of interconnection that we will have, and you will feed the data on these input sites. Okay. So for feeding the data, we will assume that during time t1, the data that we feed to this vertical input are like this: 0, 0, A13, A12, and A11. So that is one row of matrix A. During the same time T1, we have to feed in one column of matrix B to these horizontal inputs. Okay. So those are B11, B21, B31, and these inputs are 0. During time T2, I feed the second row of matrix A in this vertical input. Okay. So that will be 0, A21, A22, A23, and this input is 0, and during same time T2 I will feed the second column of matrix B to this horizontal input. Okay. So this will be 0, B12, B22, B32, and this input will be 0. Similarly, during time T3, I feed the third row of matrix A to this vertical input, and this becomes A31, A32, A33, and during the same time T3, I feed in the third column of matrix B to this horizontal input. So this input becomes 0, 0, B13, B23, and B33. Okay. And these are actually delay elements which I shown by rectangles or latches. Okay. Now, given this type of diagram, let us see how this architecture works. You find that since each of these processing elements are of this type, that means whenever you feed in A as horizontal input, B as vertical input, and C as the diagonal input, this will output A in the horizontal direction, the same thing is passed out. It will output B in the vertical direction, whereas in the diagonal direction, it will give C plus A into B. Okay. So if we assume this, if you find that at, okay, in addition to this, all these diagonal inputs are always 0. Okay. These are always 0. Okay. So find that since at time T1 we are feeding one row of matrix A in the vertical direction and feeding one column of matrix B in the horizontal direction. Okay. So once these data are available, what is the output of this processing node? That is 0 plus A11 into B11. Okay. So at this point, I will have the output as A11 into B11. Okay. What I will have here? Simply A11, and in this direction I will have simply B11. Okay. Similarly, after same time T1, what I have in this direction? Simply A12 will be passed here in the vertical direction, because this is the vertical input. B21, which is fed horizontally, that will be passed here. Okay. So what I get during T2 is, during T2, here I am feeding A21, but during T2, A12 is already available. Okay. Similarly, during T2, this B21 is already available here. The next data that I am feeding is B12. Okay. So after time instant T2, what I will get here? Here I have A12 available, here I have B21 available, and in this diagonal direction, I have A11 into B11. Okay. So in this horizontal output, in this diagonal output, I will have A11 into B11 plus A12, which is already available on this link, into B21, which is already available on this link. Okay. So here I will have A11 plus A11 into B11 plus A12 into B21 available on this link after time T2. Okay. Similarly, after time T3, what I will get here is A11 into B11 plus A12 into B21 plus A13 into B31, that will be available here. That is after time T3. And simultaneously, because this data is flowing through this pipeline, all other components will also be generated. Okay? So if you analyze this way, you will find that the output will be something like this. You will get, starting from time T6 onwards. Okay? So I'll put it like this. After T5, that is T6, during time T6, what I'll get here? C11. C11 will be outputted by this. Okay, that is after time T5, that is during time T6, I'll get C11 here. At the same time, during time T6, I'll get C21, which will be outputted by this node in the diagonal direction. During the same time T6, I'll get C31, which will be outputted by this node. Okay. During same time T6, this node will output C12, and this node will output C13. Okay. During time T7, this node will output C32. Okay. This node will output C22, and this node will output C23, and this output I will get during time T7, and during time T8, this node will output C33. Okay. And how the data will flow, if you analyze that, you will find that after time T6, simultaneously I get C11, C12, C13, C21 and C31. During time T7, I get C22, C23 and C32. And during time T8, I get C33. Okay. So as against in this case, where we have said that for this simple multiplication, matrix multiplication, I need 27 operations, the same output is obtained in just 8 clock periods. Okay. So this gives another example how pipelining can reduce the computation time. And this sort of pipelining has a specific name, systolic array. So you know that. Okay. So these two types of pipeline architectures that we have discussed, one for floating point addition and other for this matrix multiplication, you find that these kinds of pipelines are dedicated pipelines. That means you can perform only one operation with these pipelines. But it is ensured that operation is more efficient. Okay. We can have other kinds of pipelines as well, which are called generalized pipelines. Now, what is the generalized pipeline? In both these kinds of pipelines, you have seen that the data flows only in one direction. That is, from stage I, the data goes to the computation stage I plus 1. Okay. I don't have any provision of giving the data to a stage j where j is greater than I plus 1. From stage I cannot give the data to a stage j where j is greater than I plus 1 or j is less than I. That means I don't have any provision of feed forward data flow, or I don't have any provision of feedback data flow. So in case of generalized pipeline, we can have the provision of both feed forward as well as feedback data flow. So in this case of pipeline, what we have done is, or if you remember the earlier pipeline that we have done for floating point addition, we have always said that the data enters from one end of the pipeline, it comes out of the other end of the pipeline. From stage S1, the data always goes to stage 2. From stage 2, it always goes to stage 3. From 3, it always goes to 4. I don't have any facility of sending the data from stage 1 to stage 3. I am always sending the data from stage 1 to stage 2. Or I don't have any facility of giving the data from say stage 3 to stage 1. Okay? That is, I don't have any provision of feedback connection. Here in this case, from this stage, the data is always moving in this direction. Here, from here, the data always goes here. The data always goes here. That means it always goes in the forward direction following a linear path. Okay? I cannot bypass any of this. I don't have any provision of sending the data from this processing element to this processing element directly. I always have to go via this processing element. Okay. So this is a kind of pipeline which is also known as linear pipeline. The data always flows in the linear direction. Okay. In a generalized pipeline, what we will see is from any stage I can send the data to any other stage j where j can be greater than I plus 1. In case of linear pipeline, j is always equal to I plus 1. From I can send the data to j where j is always I plus 1 equal to I plus 1 in case of a linear pipeline. In case of a generalized pipeline, j can be greater than I plus 1. That means I can bypass some of the stages in between and feed forward the data. Or j can also be less than I, that means I can send the data in the backward direction in the pipeline. Okay. So such a generalized pipeline can have a structure like this. Suppose we have got 3-stage pipeline. S1, S2 and S3. If it is a linear pipeline, always data will move from S1 to S2, S2 to S3, and finally you get the output. Right? Now, if it is not a linear pipeline, and we have also said that to take care of the speed mismatch, we can put latches in between stages. Okay. So let us also put the latches. We'll have one latch here, one latch here, one latch here, and finally one latch will come here. Okay. From the latch, the data always goes to the corresponding stage. Okay. I will have an input. Okay. This stage will give an output. This will also give an output. This will also give an output. Okay. But now I have to have the provision of selecting the source of data. Okay. So as I said that in this generalized pipeline, in case of linear pipeline, the data will always move from S1 to S2. So this output of S1 can be directly connected to the input of this latch. Similarly, the data will flow from S2 to S3. So this output of S2 will be directly connected to the input to this latch. But now, in case of generalized pipeline, I can also have a provision that from S1, I should be able to send the data to S3 bypassing S2. Similarly, from output of S3, I should be able to send the data to S2. I should also be able to send the data to S1, which will be the feedback connection. If I send the data from S1 to S3, that becomes a feed-forward connection. From S1 to S2 or S2 to S3, that becomes a linear connection. Okay. So all these three types of connections should be possible in a generalized pipeline. So because now the source of data to every stage can be one of many. Okay. So I should put some sort of a multiplexer using which I can select the source of data to the input of every latch. So what I can do is I can put a multiplexer here. Okay. One input of this multiplexer is the input data, right? And output of the multiplexer is coming to the input of this latch. Okay. The other inputs to this multiplexer can be from output of S3, okay. Similarly, I will also put a multiplexer here, that is input to S2 can also come from the output of S3. Okay. So like this. And similarly, S3 can get input from S2, it can get input from S1, it can also get input from S3 itself. That is a self loop. Okay. So in this case, I can do a connection of this form. From S1, the data can go to S3, the data can come to S3 from S3 itself. So I can have a data path something like this. Okay. And each of these are multiplexers. This is a multiplexer, this is also a multiplexer, this is also a multiplexer. Okay. So we find that by properly selecting the select inputs of the multiplexers, I can send the data from output of S1 to the input of S3. I can send the data from output of S3 to the input of S1. I can also send the data from output of S3 to the input of S2. I can also send the data from output of S3 to S3 itself. Okay. So I have a reconfigurable type of pipeline. Depending upon what is the function requirement, I can choose these multiplexer select inputs so that the data will be routed through this pipeline as required. Okay. For functions, I can also perform, this can be used for computing a single function. It may also be used for computing a multiple function. That is, more than one functions can be computed by the same pipeline. Okay. So if I want to compute more than one functions, then suppose I can take an output from this test, and this gives me a function A. If I take output from this point, it gives me a function B. Okay. So there may be other connections as well. For example, in this case, we have not shown a feedback connection from S2 to S1. That is also possible. With the help of this, I can only feedback the data from output of S3 to S1. I can feedback the data from output of S3 to S2. I can also feedback from S3 to S3 itself. Okay. I can also have a feedback connection from S2 to S1 or S2 to S2 itself. That is also possible in a generalized pipeline. Okay. Now, given such a generalized pipeline, now we have to decide that because now it is reconfigurable, I have to decide that how the data path should be selected, how the data should flow to compute a particular function. Okay, which is not required in case of a linear pipeline, because in case of linear pipeline the data flow is always fixed. From stage I it will go to stage I plus 1. But in this case, because there can be various ways in which the data can flow from one stage to another, I have to specify for a computation of a particular function how the data path should be selected. Okay. So, for computing any function, I have to specify what is called a reservation table. That means, what are the time steps, what are the time periods during which of these computation stages will be used for computation of a particular function. Okay. So, reservation table can be specified again in the form of a space-time diagram. So, for example, for function A, for the computation of function A, my reservation table can look like this. There are three computation stages, S1 and S2 and S3, okay, and these are the different time steps or time periods T0, T1, T2, T3, T4, T5, T6, T7. Okay. So, when I specify the reservation table for function A, what I have to specify is during which of these time periods, which of the computation stages will be used by this function A. Okay. So, I can have a reservation table something like this. I can put a cross here indicating that during time interval T0, it is the computation stage S1 that will be used by this function A. Okay. Similarly, I can put a cross here, I can put a cross here, right. For S2, it can be something like this. For S3, it can be something like this. Okay. Similarly, to compute the function B will also have a reservation table, and that reservation table will obviously be different from this. If it is not different from this, then obviously function A and function B are same. Okay. So, for function B, the reservation table can be specified. Again, I have the computation stages S1, S2, S3. I have the time durations T0, T1, T2, T3, T4, T5, let us say we have T6, so something like this. So, let us see how the data path will be set for computation of these two functions.
Sir, if the tables are same, but the
Functions are same.
output points are different.
No, it cannot be. If the tables are same, output point is also same. So, it depends upon during the last step, last time period, which of the computation stages is being used. you find that for function A, it takes 8 different time steps starting from T0 to T7. During T7, the computation block that is used is S2. That means for function A, S2 is the output point. For function B, at the last time state T6, the computational block that is used is S3. That means for function B, S3 is the output point. For function A, the output point is S2. For function B, the output point is S3. So that is what has been shown in this pipeline diagram also. I have taken output A, function A, from the output of S2, whereas function B has been taken from output of S3. Okay. So as this reservation table says, it specifies that during which time step, during which time period, which of the computational blocks are to be used for computation of a particular function. So here you find that for computation of, say, A, during T0, the computation block that is used is S1. Okay. And this being the first one, the input obviously has to come from the external input. That means the data path that has to be active during T0 is the direct data path from the external input to this latch. And from the latch, it directly goes to computation stage S1. Okay. Then you find that during T1, the computation block that is used is S2. During T2, the computation block that is used is S3. So this follows a linear path. At least for these first 3 time durations, the data flow is linear. From S1, the data will go to S2. From S2, the data will go to S3. But after that, during time interval T3, the processing block that is being used is S1. And prior to that, we had the output available from processing stage S3. That means now I have to feed back the data from the output of S3 to the input of S1. Okay. So at this point, the path that is to be active is this one. Okay. And I have to set the multiplexer select input in such a way that now, instead of taking the data from the external input, it has to take the data from this feedback path. Okay. And from there, data will come to S1 and the corresponding computation will be performed. After S1, during time step T4, you find the computational block that is to be used is block S3. So now it does not follow the linear path anymore. In case of linear path here, from T0 to T1, we had moved the data from S1 to S2. But now we have to move the data from S1 to S3. That means I have to make use of the feed forward path. Okay. And this is the feed forward path. So you have to bypass S2, right, and set the select input of this multiplexer in such a way that the data from this input will be selected and that will be fed to the computation block S3 for this part of computation. Okay. And this way the computation will continue, and at the end of T7, you get the output from the computation stage S2. Okay. Similarly, we can also find out how the data flow will be performed for this function B. So it is this reservation table which specifies that how the data will flow through the pipeline and how many times it will be fed back or feed forward to compute a particular function. Okay. And obviously, the pipeline control circuit, which decides that how the multiplexer select inputs will be decided or how the data will be latched into different latches, that will make use of this reservation table, because it is only through the reservation table the control circuit will know how the data has to move or how many time steps will be needed for computation of a particular function. Okay. So this reservation table is very important for a generalized pipeline.
So we are assuming that all The blocks are essentially performing different functions,
Yeah,
and they have different delays for each block.
they will have different delays.
Sir,
This is a
They have
generalized one.
same delays.
No, not necessarily. Blocks can have different delays, but the final delay, I mean how much delay is allowed, that is decided by the control circuit. It is the control circuit which will decide that when to latch the data from one stage to the latch. Okay, and that takes care of what is the maximum delay in defined stage.
So here at a particular time is spent, only one block is working, sir. So sir, where is the
At a particular time instant, only one block is working for these functions, but it is not necessary. I can have a situation like this as well. This is also possible in a reservation table. That means for computation of function A, during time step T3, you are making use of both the computation stage S1 and stage S3. Okay. So if you do this, you find that during time T2, during time step T2, S3 was used. So after time step T2, the output is available from S3. During this time, both S1 and S3 are being used. That means I have to set the multiplexers in such a way that is that output of S3 goes to both S1 as well as S3 itself.
But there is no use of using both of them there. I mean, if you are using just S3, then we are not using the output of S1 after that.
Going from S3 to S3 itself, going to S1 also.
Okay.
Yeah.
But after that, you are not using. I mean, you can go back. So we won't be needing the output of S1 after that.
Why?
So we are generating two sets of data.
Potensial, that you don't need output of S1.
You are not needing in the diagram. So one student must have two input.
This is giving an output. Okay. Then after that, the stage which is being used is S3.
So it's either S3 to S3 or S1 to S3 after that.
Okay, you are talking about this multiplexer. Maybe some more function will be generated here. That is also possible. Instead of a simple multiplexer, I can have a functional block. So multiplexer will be a part of that functional block. Or maybe before S3 I have one computation stage which will combine these two outputs, output of S3 and output of S1. What I have shown is a very, very simplified situation, but this can be complicated. Okay. So in case of generalized pipeline, it is possible that more than one computation stage will be used during the same instant of time. That can be done. Not only that, in a complicated situation, it is also possible that the pipeline is being used for computation of more than one function simultaneously. That is also possible.
If there is no.
But how to do it, that you have to find out. That has to be found out by analysis of the reservation tables. Okay. Now when I come to this generalized pipeline, here you find, in case of linear pipeline, I didn't have any problem. At every time step, I can feed in a new data, a new task to the pipeline. But when I come to this generalized pipeline, that is not possible. By studying this reservation table, I have to find out that what are the time steps when I can feed in a new task to the pipeline. I cannot feed in a new task to the pipeline at every time step, because in that case there can be data clash. How? See, for example, here, for computation of a particular function f a, function A, the pipeline makes use of this computation block S1 during time instant T8. It makes use of the same computation stage S1 during time instant T3. It also makes use of the same computation stage S1 during time instant T6. Okay. So if at T3, during T3, I want to feed in a new task, a new set of data, but on which the same function A has to be computed. Okay, then you find that this T3 becomes T0 for that new task, right? So for the new task, S1 has to be used simultaneously when S1 is also being used by the previous task, which is not possible. That means two tasks are trying to use the same processing stage S1 at the same instant of time. So obviously there will be clash. Okay? So that is what is called pipeline scheduling. I have to decide when I can schedule a new task to the pipeline. I cannot schedule a new task to the generalized pipeline every time, which I can do in case of a linear pipeline. Because in case of a linear pipeline, I know that the data enters one end of the pipeline, it goes out of the other end of the pipeline, and in between it always has a linear flow. That means from S1 it will always come to S2. For the same function, S1 will not be used again. Okay? So at every time step, I can give a new task to a linear pipeline. I don't have to consider about this collision. I don't have to bother about this collision. But in case of a generalized pipeline, I have to find out that what are the time durations or what are the time steps when I can feed in a new task to the pipeline. And that I have to do by analysis of this reservation table. Okay? So now let us see how we can analyze this reservation table. So one thing I have said that here, if I initiate a task at T0, I cannot initiate next task at time instant T3. Because then there will be clash for this process stage S1. Neither I can initiate a task at time instant T6, because then also there will be a clash on S2, on S1. Similarly, here I cannot initiate a task at T1, if at some instant of time at T1, this function A makes use of this processing stage S2, I cannot initiate a task in such a way that the next task will make use of the same processing stage S2 during time instant T7. Because then there will be a clash in this processing stage S2. Okay. So I have to analyze this reservation table so that at no computation stage there is a clash. Okay. So only when I know that by initiating a task it does not lead to any clash, I can initiate a new task at that time instant. Okay. And that can be found out only by analysis of this reservation table. That we'll do in the next part.